All right, so in this section, we're going to talk about solving literal equations. So, what's a literal equation? In the real world, we've got a lot of scenarios where we just use an algebraic equation. Like, for example, if you're going somewhere, driving, and you know how fast you're going, and you know how long you drive. So, if you go 60 miles an hour for, say, 4 hours, then you just do 60 times 4 to give you 240 miles. And so we actually have an equation for that in physics. It's one of our basic kinematics equations. And what it says is that the distance that you travel, can be calculated by taking your rate, which is your speed, like miles per hour, and multiplying by your time in hours, however long it took you. Or, if you're like from across the pond, you would measure it in meters per second, and then you would figure out how many seconds you've been traveling, and you could figure out your distance in meters. So we've simplified this down to a nice, easy equation here, namely that d distance, with d, which stands for distance, is equal to r times t, where r is your rate of speed, like your miles per hour, and t is your time in hours. But you can change these units to anything you want. Meters per second, feet per minute. That'd be a weird rate, but whatever. And so what's nice about these is if you have d is equal to rt, maybe let's say if you know the rate of speed, like your miles per hour, and how many hours it's going to take you to get somewhere, you can calculate distance. You just do r times t. But it's really nice in some scenarios, like let's say you have a distance, and you want to make sure that you get there in a certain amount of time, and you want to actually figure out how fast you need to go. So like the distance, the time that you want to spend driving, then you can figure out what the rate is. And look, most people, this is pretty intuitive. Like, you can just take your distance and divide it by your time, and that'll give you the rate. But that's the whole point of this section here, is we want to be able to solve for a variable, get a variable by itself, so that we don't have to think about it. We can just plug in numbers. Okay, so they want you to solve the equation for r. So what's annoying about this is there are literally no numbers in this. So it's all letters, but we're going to approach this the same way that we've been approaching the last few problems, right? If we had 2x minus 6 is equal to 8, we're going to add 6 to both sides. We're going to divide by 2 on both sides, and that'll give us our the variable that we're looking for. We're just not going to get a number on these kinds of problems. We're going to get just letters, but that's okay. So I'm going to undo my writing here, and then we're going to go ahead and solve for r here. So if we're solving for r, if the goal here is to get r by itself in this equation here, what do we need to do? T is the only thing that is preventing r from being by itself. And what is t doing to r? It's multiplying. So we're going to divide by t on both sides. So when you do this, you get that d divided by t is equal to, those t's cross out there, t divided by itself is 1. And so what you get is that the rate, r, is just the distance divided by the time, which, again, this is not super profound. Like, usually you just think about it, you're like, oh yeah, that makes sense. But this is really helpful in if you know your distance and your time and you want to know the rate, you can just do d divided by t. You don't have to go in here and think about it and work backwards. Okay? So step 2 says use your new equation to determine the rate of speed for someone who took 3 hours to travel 210 miles. So we already know that we're doing d over t. So in this case, we're going to say 210 miles over 3 hours. So what is that? That's 210 over 3 is 70, and then it's miles per hour, right? Miles divided by hours, miles per hour. So, okay, a fairly simple example, but it helps illustrate the point there. So you're like, okay, well, that's fairly simple. Then you get into some more complex examples. So like in physics, when you have two objects, like a couple planets or something like that, they exert a significant amount of force on each other. Or, the sun and the earth. Like the sun and the earth actually pull each other toward each other. And you can use this equation to figure out exactly how much force those two bodies exert on each other. In fact, everything in the universe exerts a force on every other thing in the universe, a gravitational force. It's just so small that you don't really detect it. So, okay, so basically this equation here, you don't really need the multiplication signs. The idea here is that you have F is equal to G times M1 times M2, and it's all divided by R squared. Okay, so G is the gravitational constant. It's just a number. It's a really, really small number. And then M1 is the mass of the first object. M2 is the mass of the second object. And R here is the distance between the two objects. And because we do this in the metric system, the masses are in kilograms instead of pounds, and the distance is in meters instead of miles or feet or, whatever. So what they want us to do here for step one is they want us to solve the equation here for M1. They want us to get M1 all by itself. Okay, so let's go ahead and let's come down here and let's actually write out the equation again. I don't know why it's not letting me zoom. There we go. Okay, so let's write out our equation here. G is equal to, or not G, F. The force between two objects is equal to the gravitational constant times M1 times M2 over R squared. And our goal right now is to get this guy, M1, by itself. So what do we need to do? How are we going to manipulate this to get the M1 alone? So what I would recommend first is I would recommend multiplying to get rid of the R squared on the bottom there. Okay? So on the left side you have R squared F. If you write F R squared, that's fine. On the right side you have G M1 M2. Okay, so your R squareds basically cancel each other out there. It's an equivalent form of 1. And on the right side you're just left with G times M1 times M2. On the left side you have R squared F. And what was our goal? Our goal was to solve for M1. So we're still trying to get M1 all by itself here. So what do we need to do to get M1 by itself? We need to undo what's being done to M1. What's being done to M1 right now? It's being multiplied by G, and it's being multiplied by M2. If you want to divide them one at a time, you can do that. But I find it's very easy to just divide by everything in there. So we're going to divide by both of those at the same time. When you do that, the G's will knock each other out, M2's will knock each other out, and you're just left with R squared F over G M2. That's equal to M1. So in a scenario, if you knew the distance between two objects, the force they exert on each other, the gravitational constant, and the mass of the second object, you could calculate the mass of the first object. This is seems like weird and like who cares, why would I ever need this, but it's actually very useful to have for engineers and physicists and astronomers and all of that. Okay, so that was step one. Step two, they want us to solve the formula for G. So they want us to take the original formula, and instead of solving for M1, we'll solve for G. So it'll be very similar, actually. G M1 M2 over R squared. So now the goal here is instead of getting M1 by itself, we're going to get G by itself. So it's actually going to be very similar to what we just did last time. So if there's a fraction, I like to get rid of the fraction first. So I'll multiply by R squared on both sides. So we'll have R squared F is equal to G M1 M2. And just a reminder, the goal is to get G by itself here. So what do we need to do to get G by itself? Like what's currently being done to G that makes it not be by itself right now? It's being multiplied by M1 and M2. So let's go in and divide out the M1 and the M2 at the same time. M1, M2. And when we do that, those knock each other out. Those knock each other out. We're just left with R squared F over M1, M2. Apparently that's equal to G. So there you go. This is actually how they derived their gravitational constant. They noticed that there was a relationship between two objects and the force that they exert on each other, and then this is how they solved that. So, all right, let's move on to the next page. So you guys probably don't have to worry about this year, but in chemistry, you'll probably take your sophomore, junior, senior year at some point. There's a thing called ideal gas laws. So one of the gas laws is that the pressure of the gas multiplied by the volume of the gas is equal to the number of moles that are in the gas times the ideal gas constant times the temperature of the gas. Except they don't measure it in Fahrenheit, they measure it in Kelvin, which is a little more complicated than Celsius, but Kelvin actually makes the most sense as far as temperature goes for measuring things. But hey, this is America. We do Fahrenheit, so. Okay, so they have a nice little equation here. PV equals nRT. You're going to see this a lot. For some reason, we capitalized the V, and a lot of the other variables are left lowercase, so whatever. They want us to solve the formula for N here in step 1. So, all right, so PV equals nRT, and they want us to solve for N here. So this is actually pretty easy. If you're going to solve for N, you just need to undo what's being done to N here. So in this case, N is being multiplied by R and T. So if we divide out R and T at the same time, that'll give us N. Okay, so N is equal to PV over RT. This will be very useful for you when you get to chemistry, being able to this is called isolating a variable. So you're getting a variable by itself, even though there aren't numbers per se. Okay, solve the formula for T. All right, let's do it. So PV equals nRT. And the idea here is we're solving for T, so we want to get the T all by itself. So what's being done to the T right now that's preventing it from being by itself? It's being multiplied by N and R. So let's go ahead and divide by N and R at the same time. When you do that, the N and the R cancel, and you get PV over NR. That's equal to T, the temperature in Kelvin. Okay? All right. Last example here. So in geometry, you guys are going to cover this next year. When you have a trapezoid, a shape like this, where you've got two sides that are parallel, and then you've got two other sides connecting them, you can find the area of a trapezoid. We've actually figured this out. So there's a nice little formula. So it's very similar to the triangle formula, actually, right? You know the area of a triangle, 1/2 base times height. So the area of a trapezoid is very similar. It's 1/2 of the bases added together times the height. So this is base 1, this is base 2. So this formula will allow you to calculate the area. Sometimes it's actually helpful if you already know the area and maybe the height and one of the bases. You want to find the other base. What you can do is you can solve this backwards to get whatever it is by itself, and then you can just plug in numbers. You don't really have to think about it too much. Okay, so step 1 says they want us to solve for B1 here. So let's do that. So the area is 1/2 of the height times B1 plus B2. These little guys are called subscripts, by the way. I don't know if you guys are familiar with these. They're not numbers. They're just indicating the first base versus the second base there. So it's just helpful to know. Okay, so they want us to get B1 by itself. So many of you are going to be tempted to subtract B2 here. You can't do that because it's B2 is being multiplied by several things here. So instead of subtracting, what we're going to do is we're going to multiply here in order to we're going to multiply and divide because we're trying to get rid of the 1/2 and trying to get rid of the H. Then we can subtract the B2. So in order to get rid of the 1/2, we're going to multiply by 2 on both sides, because when you multiply by 2 and divide by 2, those cancel each other out. So you get 1 basically. So 2 divided by 2, those will get rid of each other. So you're left with 2A on the left is equal to H times B1 plus B2. And now the question is, so we don't want to subtract B2 yet because it's being multiplied by H. How do we get rid of H here? If H is multiplying this expression, the way to get rid of H is to divide by H. So we're going to divide by H on both sides. So when you divide by H on both sides, those two cross each other out. You're left with 2 times the area divided by the height is equal to B1 plus B2. And so now the question is, what do we do to get B1 by itself? So B1 is here. Right now B2 is being added to B1. So in order to undo that, we are going to subtract B2 from both sides. Okay, so it's a kind of an ugly formula, but what you get is you get 2a over h minus b2, and apparently that's equal to b1. So if you ever want to know what the first base is, if you have all the other variables, like if you know the area, the height, and base 2, this formula would be able to calculate that for you. Okay, and then the last step here, so using your equation from step 1, find the length, b1, of a trapezoid. If you know the area is 24, the height is 2, and the second base is 4. So, okay, cool. So we'll just go in here, and what we'll do is we'll say, okay, I know that 2a divided by h minus b2 is b1, and then I'm just going to plug in the numbers they gave me here. So I'm just literally going to plug in all of the things they gave me. So they said the area was 24, so I'm going to put that in. They also told me that the height is 2, right? And then they also told me that the second base was 4. So we got 48, 2 times 24 is 48 over 2 minus 4. Whatever that is, that's going to be the first base there. So, okay, so 48 over 2 is 24, minus 4 is equal to b1, so b1 is 20. 24 minus 4 gives you 20.